modern additive manufacturing has, in recent years, really grown exponentially in terms of what can be achieved. So it's really no longer just a method to kind of produce visualization aids or prototypes. In fact, AM has really opened up possibilities for product design that, only a few years ago weren't really even contemplated. So we can now use kind of organic designs almost completely without limitations. We can manufacture almost anywhere needed, so think about out at sea or under the sea, in deep space or in crisis zones. And then we can use modern scanning technology and we can make new parts for really any situation at the push of a button. So it's really opening up a lot of kind of amazing ideas for what is possible with additive manufacturing. So when we look at kind of the challenges for additive manufacturing, we really kind of look at historically design type of tools separate from simulation tools or tools about how a part is going to perform in the field. So design for additive is kind of largely looking at things like generative design tools, topology optimization, geometry reconstruction, functional lattices. And then on the field performance side, the challenges are usually in kind of accurately capturing loads, assessing, things like crack initiation or durability. But for additive manufacturing, the build process really kind of introduces many factors that we kind of need to consider when we're moving from our as designed part to our as manufactured part. So things like the support structures in the build, the tool path that you use, those can really largely affect your resulting part distortions, your residual stresses, your surface finish. And then another issue that happens is that the material properties of your as manufactured part can also be largely affected by your build process. So things like microstructure evolution, grain growth, and nucleation might also be need to be accounted for to really fully understand how your as manufactured part is going to behave in the field. So now that we kind of understand, okay, these different challenges that the AM process introduces, can we translate these to kind of engineering questions that we could use, say, simulation software or engineering software to solve? So can we make a structure, 50% lighter and 50% stronger at the same time? Can we print spare parts with, in-service quality on site, wherever that part is required? How is our production lines affected if a machine fails? And how many parts can we print per hour if we want those parts to have, a specific strength requirement? And then finally, can we achieve durability? So these are really kind of the specific engineering challenges that we need to address. And we kind of look at this in the big picture. We see that, engineering software solutions to answer these challenges will really need to have kind of a broad capability for, design, manufacturing, and simulation. So Dassault Systèmes has really a wide portfolio of engineering technology, and we're working towards really enabling all of this technology on the 3DEXPERIENCE platform. So we have things like a kind of a broad spectrum of simulation tools that cover, all physics, so fluids, structures, electromagnetics, looking at even different scales for simulation. We also have smart manufacturing tools. And so the 3DEXPERIENCE platform really kind of helps engineers connect within their extended ecosystems. And this connected platform really kind of eliminates the concept of data transfer. And that is what allows engineers to really be more efficient in their engineering roles. So in the additive manufacturing space, where a lot of the software tools are specialized and disjointed, the 3DEXPERIENCE platform can really offer a lot of efficiency gains, and we're going to talk about these as we kind of progress through the webinar and look at the different tools. Okay, so first I want to talk to you kind of the overall Dassault Systèmes additive strategy, which actually we outlined in 2015, and we've really been working towards enhancing the technology over the last several years. So this strategy kind of centers around 5 key themes. So the first one is the 3DEXPERIENCE marketplace, and this is to really connect the community. So it's kind of a transactional space which is based on services that Dassault Systèmes and other kind of partners within our ecosystem offer. And we'll talk in more detail about this. So the second theme is kind of materials, and we really believe that materials are core to kind of any additive process. And designing materials kind of from first principles using molecular dynamics, quantum mechanics type simulations is really critical for AM, whether you're looking at polymers or metal alloys. So the third theme is function-driven generative design, and we'll look at this this application in detail. And then the fourth is kind of process definition and production planning, so how we do our manufacturing planning and our simulation. And we'll again look at this this theme. So the last kind of theme is the global production system, and it's kind of how we think about additive manufacturing farms or factories, where you have kind of that entire process of manufacturing and machining to get to your final part. And how can we manage those factories to have kind of production be happening in an optimal manner. So this is kind of all of the technology that we have enabled for this AM strategy. So let's kind of look in detail at some of these. Okay, so launched earlier this year, the Dassault System 3D Experience Marketplace. It really kind of empowers you to collaborate with a qualified set of industry service providers. And they offer a range of, kind of different services that you are going to need throughout your product development process. So the first of the two marketplace services that we provide consists of what we call Marketplace Make. And this is for on-demand manufacturing, and this is across all manufacturing processes, so not just additive necessarily. The second piece of the marketplace services is part supply, and this is for intelligent 3D component sourcing. So these marketplace services you can access directly from SolidWorks, CATIA, or the 3DEXPERIENCE platform. So this really kind of lets you connect to this space within a design environment that you're kind of comfortable with. So depending on what you need, each of these marketplace services, so Make or Part Supply, kind of consists of consists of both a community offering, and think of that as being kind of public and accessible to everyone, but there's also an enterprise service offering, which really gives organizations some kind of additional value to let them have control over their kind of internal and external ecosystems for that process of design through manufacturing processes. So the videos here show Marketplace, Part Supply, and kind of the comprehensive 3D part catalog that you can use to source your different part needs. And then Marketplace Make kind of gives you a direct connection with leading kind of rapid response suppliers, and those suppliers already have kind of proven track records for delivering fast production parts. So you can really kind of take your parts through this whole digital thread idea from concept to production, and we can access all of this through these applications that we're discussing with. Okay, so first, we're going to look at this functional generative designer application. The tools in this application are really kind of changing the paradigm from just checking that your design meets its requirements to actually using optimization tools to find a design that best meets your requirements. So the main advantage of this application is really kind of this combination of a robust optimization solver coupled with powerful but really easy to use geometry reconstruction tools. So let's kind of discuss the new functionality in 2018X that's available for this functional generative designer application. So the Generative Designer tool in 2017 also had a one-click function for generating smooth reconstructed geometry. However, in 2018X, we have added some improved smoothing algorithms, and these can help the designer get to a reconstructed geometry much faster. So a geometry reconstruction step that may have taken several hours can now be achieved with this kind of one-click functionality. So we see, our improved smoothing algorithm provides a much smoother automatic reconstructed geometry shape compared to what we had previously available. The ability to include prescribed temperatures has also been added to the functional generative application, and this kind of lets you account for things like hot or cold load cases in your optimization. So we also have some new envelope plot capabilities, and these really help you understand, which load cases are impacting different areas of your design through kind of this color coding and these envelope plots. Okay, so another new functionality for generative design in 2018X is the ability to optimize multiple components at once in an assembly. So since the optimization of just a single part can kind of end up just shifting the loads around between different components in an assembly, we really need that ability to optimize multiple parts simultaneously to make sure that the entire assembly performs as optimally as possible. So in this workflow for assembly optimization, first you define your design space, and then you mesh all of your components in your assembly, and then you specify both local and global optimization targets, and then finally you can kind of generate these concept shapes for each of these individual components. Okay, so next we're going to talk about some of the new optimization constraints or enhancements to optimization constraints that have become available in 2018X. So we have a new overhang constraint that's now available, and this is really specifically for additive manufacturing. So for this constraint definition, you first specify your design space, you specify a print direction and a minimum overhang angle. So the optimization is then going to account for this overhang angle, and this is going to help you achieve a design that does not require support structures to be built. So we know for additive, not requiring support structures can really help immensely with manufacturing post-production of these AM parts. So being able to account for this in our part design optimization is a really beneficial thing. So we already had existing milling constraints available for the optimization, but we have some new capabilities for automatic geometry reconstruction of milled parts. So these new tools kind of let you use those defined milling directions for your optimized part, and it's going to create the pocket sketches and the final geometry for that part automatically. So really kind of some automatic geometry reconstruction tools for our existing milling constraints. Okay, so the next application or role we're going to talk about here is the additive manufacturing programmer role. And if you recall, this is kind of where we plan for the additive manufacturing build. Out of the box, this is set up for powder bed fabrication processes, and this is where we first capture the manufacturing environment with process reuse, and then we do our process preparation type operations, so things like part orientation, optimization, generating support structures, generating slicing and scan paths, and then finally we use those outputs from this build that we've planned to either send directly to a printer, or we can use them for process simulations. So now we'll take a look at some of the new functionality associated with process planning. Okay, so in terms of part orientation, we have some new capabilities for optimization criteria that are now kind of available in 2018X. So we have introduced some new criteria, but we've also introduced the ability to kind of incorporate weighting factors so that you can consider multiple criteria at once. So this allows you to, say, compute the best build orientation of a part by looking at both, minimizing build height and minimizing the area of the part to be supported. So you can really just put weighting factors on the different optimization criteria, and we've introduced some new optimization criteria as well. So we have also introduced, some new collision detection tools. So when you're kind of manually positioning the parts on the build tray, there are tools that tell you if parts are too close, if parts are outside of build domains, things like that. And we also have some new capabilities for part orientation, so things like you can specify if you want a part to be parallel, or a given surface on a part to be parallel with the build tray, or orthogonal. We have those capabilities now, and then you can also reuse some of the prior orientations that you've used for new parts. So finally, there's also new capabilities for being able to nest as many parts as possible on the build tray. And so to include these capabilities, we have also incorporated the ability to define exclusion zones. So you can create zones where you don't want parts to be nested or parts to be created on your build tray in those zones. And then you can use these automatic nesting tools to kind of pack as many parts in there as possible while honoring those exclusion zones. So we've got these exclusion zones that we've specified, and we can kind of do our automatic nesting from there. Okay, so also in 2018X we have some different capabilities regarding support structures. So we've given the user some abilities for manually selecting the regions for the support structures. So you have some freedom now in defining, where you want to have support structures between, different components in your model, build tray part, things like that, or between, say, nested components. We've also given the user the ability to kind of manually modify the support structures that are automatically generated. So you can either kind of locally recompute those support structures with different parameters, or you can, remove any support structures that are automatically generated, or you can kind of modify the nodes of these tree type support structures. So one of the main advantages of these process planning tools on the 3DEXPERIENCE platform is that the data related to a specific printer and or a specific material set and printer can really be contained within what we call this additive manufacturing virtual machine. So the virtual machine is a searchable and programmable PLM object, and so so it has its own data class in the system, which makes it easy to find, easy to populate, and we're working with different machine vendors to kind of ensure that we have an accurate and complete version of different machines, different material sets for these virtual machine libraries. Okay, so next I want to introduce you to a new application for manufacturing planning, and this is going to be kind of generally available in 2019X. So this application will be called the Material Deposition Programmer, and it's really designed to program things like polymer extrusion or directed energy deposition machines, and these are typically kind of driven by G-codes. So we have been prototyping this application with Cincinnati for their BAM process, and we're working on kind of having more custom post-processor functions become standardized within this application. Okay, so finally, I want to introduce you to some new simulation capabilities that we are going to incorporate into a new powder bed programmer application in 2018X. So we talked about this workflow for the powder bed fabrication application where you define your build setup, so things like your build orientation, your machine parameters, and then you move to generating support structures, and then you move to kind of generating that laser path. So at this point we can kind of branch out in this workflow. So in 2017X, we have, historically had this additive manufacturing researcher application. And this is where we use that build setup information from, from all of this planning, steps 1, 2, and 3, to do a full thermomechanical simulation of the build. So what we're introducing now in 2018X is a new Eigenstrain capability. And this is going to be incorporated into this kind of manufacturing planning flow in the powder bed programmer application, and it will act as kind of a simple means of checking distortions with some automatic model setup in there. So we're going to discuss these simulation capabilities in more detail next, and I'm actually going to pass the presentation over to Jing so that she can kind of give us some more details on these simulation capabilities.
All right. Thank you very much, Rachel. I'm going to go ahead and show my presentation. Now let me continue on to the virtual printing parts of the solution. We first released the Additive Manufacturing Researcher role in July last year. We released a guided user interface for the powder bed process, and this interface walks you through the steps required to build a thermomechanical process simulation model. Because designers and manufacturing engineers, they're both interested in the process simulation and they are with different levels of expertise in finite element analysis, we created the guided interface to contain simulation best practices, so it is practical for non-simulation experts to use it as well. Underneath this simple guided user interface is a powerful general-purpose simulation framework developed by our established Abacus solver technology. The framework allows us to perform multiple levels of simulation within the tool, so we are able to look at detailed process level simulations for microstructure, parts level simulations for distortions and residual stresses, and build level simulations to capture interactions between different parts on the build tray. The framework is also configurable for different AM processes, such as direct energy deposition, polymer extrusion, binder jetting, and other processes. Real value in process simulations for additive manufacturing comes from the ability to arrive at a successful build configuration without physical trials and errors. But for this to be possible through simulation, the run times must be significantly faster than build times without a significant loss in the accuracy of the results. Because our simulation framework allows for the solution fidelity to be controlled simply through the mesh sizes and time incrementation, we are able to study and quantify this trade-off in solution accuracy versus performance. We have characterized the levels of solution fidelity as design through production to analysis, where design is a fast solution that requires aiding design decisions, and analysis is refined solution of one build layer per time increment. The chart on the left side shows the time for a design level simulation, and the numbers on the chart are scaling factors on the design level solution for the other levels of fidelity. For example, for this turbine blade model, the design level simulation can be run in 33 minutes, and the production level simulation is about 4.2 times the design simulation, which is 4.2 times 33 minutes, and the actual build time is 35 times 33 minutes. So this chart gives you an idea of the simulation times comparing to the physical build times. The chart on the right shows the loss in the accuracy of peak distortions for these different levels of fidelity. We can see that for the three parts studied here, we can get a solution within 80% of accuracy in under 2 hours, even for large parts like parts with over 8,000 build layers. After the additive manufacturing build simulation, it is often necessary to simulate additional post-processing that is done to the parts. For example, wire EDM to remove the part from the build plate, or heat treatment to remove the residual stresses, or other final machining processes. We see here that we can use progressive material removal to simulate wire EDM. We can also use progressive material removal in the same context as using progressive material addition according to a machine tool path. Besides, we can apply heat treatment thermal cycles to simulate the reduction of build stresses. We can also predict in-service durability of the additive manufacturing parts with consideration of print process-induced residual stresses. So these are things that we already introduced by end of 2017. Now, let's focus on the new capabilities coming up in 2018X. So one of the major difficulties that we've been hearing from customers is that sometimes they encounter when they're working in additive manufacturing is the geometry exports from machine softwares. A lot of the times we would obtain scanned mesh files instead of full geometry files for extremely complex shaped parts. We would like to introduce the new Voxel mesher in the 3DEXPERIENCE platform with meshing technologies from CST, which is an electromagnetic company that we acquired in 2016. That's been used for many decades, the technology in CST. So the new Voxel mesher in 3DEXPERIENCE delivers robust meshing solutions. It will now be available to generate voxel meshes out of non-native geometries or scanned geometry files such as STL files. We can generate either cubic voxels with user-specified mesh size or voxel mesh with specified XYZ mesh sizes, as well as coordinate system in which the mesh stacks in. Now, let me introduce a completely new approach to do virtual printing process simulations, the Eigenstrain method. Again, we have made the same guided user interface for Eigenstrain method in additive manufacturing researcher role, users will be able to choose from either thermomechanical approach or Eigenstrain approach when switching to the additive manufacturing researcher role here. Upon selection of the new Eigenstrain method, users will be entering a new guided interface for setting up Eigenstrain method process simulation model. Similar to thermomechanical approach, users would usually start with meshing, material application, applying tight constraints, and boundary conditions. The difference is that users do not need to set up the heat transfer analysis or apply thermal history from a heat transfer analysis to the stress analysis. Instead, users would import a predefined Eigenstrain library that includes Eigenstrain tensors for different scan patterns, scan speed, and scan power. Users are also provided with simplified approaches to define material activation. Material activation can now be directly defined by bounding boxes and slice height and start and end time of the build. Detailed machine toolpath is not required to set up the Eigenstrain process simulation if you're using the pattern-based Eigenstrain method. Scan patterns can be assigned to local regions by bounding boxes. Or trajectory-based Eigenstrain process simulation can also be used to assign local scan patterns automatically if detailed machine toolpath is available. So by providing both thermomechanical and Eigenstrain process simulations, we make sure that users at different enterprises with different accessibility of experimental and machine data can use process simulations based on their needs. For example, if for an enterprise who has access to a built-up Eigenstrain library, using the Eigenstrain eventually could enable faster development cycles. For researchers who are looking at microstructure and complex deformation modes, the thermomechanical approach is a better choice. Now, what is Eigenstrain? We believe that helping users to understand the essentials of Eigenstrain method would help them make better choices when to use it. Eigenstrain is often referred to as inherent strain or assumed strain or stress-free strain. It is an engineering concept to model residual stresses and distortions. In a linear elastic deformation, the stress introduced by eigenstrains can be represented by the constitutive equation as shown on the screen. Eigenstrains are used to compute residual stresses coming from mechanical, thermal, and microstructure sources such as phase change. Thermal strains are a subset of the eigenstrains. An eigenstrain in 3D is represented by a standard strain tensor with 6 components. The components of the eigenstrain are functions of many factors, including material properties, manufacturing process, and thermal history. So the question really is, how do we create the eigenstrain library? There are various methods that can be used to determine the appropriate eigenstrains. For example, on destructive or non-destructive tests of manufactured parts for the thermal strains, numerical simulations, or analytical formulas, but only for simple scenarios. So once an appropriate eigenstrain field has been determined, it can be applied in a layer-by-layer simulation to predict the residual stresses and distortions for a 3D printed components. So the direct benefit of eigenstrain method is the elimination of heat transfer step as compared to the thermomechanical method. This itself saves the modeling and simulation time for the heat transfer step and cutting down nearly half of the cost. The eigenstrain approach also eliminates the need for obtaining detailed machine toolpath information, which sometimes is a headache for our customers. With simple definitions of layer thickness and build time, we can perform process simulations. However, the eigenstrain method does require predefined eigenstrain libraries, especially when a variety of scan patterns, speed, and powers are used. It is sufficient to capture distortions and residual stresses, but may not capture higher order deformation modes such as the buckling modes that may happen to some thin-walled structures during the build. Therefore, the users should really choose the method to use based on what they have access to. For example, if they have access to a built-up Eigenstrain library or not. So if they have the access to a built-up Eigenstrain library and don't have access to a detailed machine toolpath, then using the Eigenstrain will be a good choice. Otherwise, using thermomechanical procedure will still be more accurate for higher order deformation modes capture and any microstructure predictions that requires detailed thermal histories. So we talked about the three methods to obtain Eigenstrain library, including experimental, numerical, and analytical. Now, we show a numerical approach that can be easily used to obtain the Eigenstrain library. The generic procedures to calibrate Eigenstrain numerically would still require experimental testing, but not in a way that requires complex thermal strain measurements. This can be done with somewhat simple cantilever prints and distortion measurements. First, starts by listing the scanning strategies that you might have for your later builds, such as different scan speed, scan power, and patterns, in order for you to create the Eigenstrain library. So print a cantilever beam with each specific set of the machine parameters, and after the print, cut the supports and measure the distortion along the center line of the top surface. Set up a corresponding simulation model in the 3DEXPERIENCE platform using pattern-based Eigenstrain method, and run the simulation through a process composer workflow. Provide the physical measure data, calibrate the Eigenstrain tensor components to minimize the gap between your distortion from experimental measure and the numerical simulation. So we show on the right a validation example we did with the Renishaw case study. We calibrated an Eigenstrain tensor for both 0 and 90-degree scan patterns and another Eigenstrain tensor for rotating 67-degree scan pattern. We simply used lump simulation layers to make it faster. So here we show the calibration result using a single Eigenstrain tensor that is validated for both 0 and 90-degree scan patterns. It is shown that both thermomechanical approach and Eigenstrain approach matches with the experimental measured distortions after the support cutting. The deformation mode and the magnitude are matching very well. It is also shown on this slide that using same approach, another Eigenstrain tensor was calibrated for the rotating 67 scan pattern. And again, both thermomechanical and pattern-based or trajectory-based Eigenstrain methods match very well with experimental measured distortion. After the support cutting, the deformation mode and magnitude matches very well. So those Eigenstrains, we went ahead and used it You apply the calibrated Eigenstrains and use it for this realistic aerospace turbine blade model. The results from thermomechanical and Eigenstrain methods prove that the effective use of Eigenstrain methods for process simulation for realistic and complex parts. So with the growing Eigenstrain library, the Eigenstrain approach can become handy for continued use as users move forward further in additive manufacturing. The thermomechanical, on the other hand, show high value in prediction of higher order structural deformations using during the print, such as buckling and capture of the microstructure phase transformation and resulting final material behavior. Last year, we also introduced the reverse shape optimizer role, which can be used for shape compensation. Effectively, this tool allows us to morph a CAD object using point cloud data. For example, we can morph a CAD object using process simulation distortion results and compare in a deviation analysis between the simulation results with the experimental obtained measurements. This allows us to validate our process simulation distortion results with the experiments. We can also negatively compensate a CAD object with predicted distortion fields. So then the printing of this negatively compensated geometry would result in reduced build distortions. And we can iterate that until we reach a tolerance for the part. Today we've added the new vector field transformation tool to this role. With this new tool, you can specify the coordinate system for the FEA result and the part in the design. So the vector field transformation will automatically match your distortion field from your simulation to the part in design. So there is no manual handling of matching of the distortion field with your design anymore. Now, it is important to point out that all our solutions for additive manufacturing and the latest updates that has been discussed above are available both on-premise and on cloud, and with high-performance computing capabilities. We provide flexible licensing for burst and sustained usage via the cloud. Customers have faster access to the infrastructure, improved IT efficiency, and greater geographic reach, and ultimately faster time to market. So how do we achieve it? We achieve this by introducing the all-inclusive 3DEXPERIENCE cloud offer, including all of the 3 services. For example, traditional independent software vendor services provided, usually either 1 or 2 of these options, such as the infrastructure as a service or software as a service. The Source System is the only company that provides a complete cloud solution encompassing from infrastructure to platform and to software. So SaaS is short form for Software as a Service. This is provided by industry solution experiences, industry process experiences, and roles. PaaS, which is Platform as a Service, is provided by the 3DEXPERIENCE platform. We also provide the infrastructure as a service via DS hardware. These include hardware, computer, computation, storage, and networking, etc. So this is turnkey solution for the end-to-end additive manufacturing. Users don't have to deal with a bunch of vendors for software and hardware sides. The Source Systems is uniquely providing all these 3 services. Again, no other independent software vendor has this ability. In summary, we hope we have unfolded our additive manufacturing solutions to enable you to print functional parts via our strategy, our technology, and our applications. Our strategy is end-to-end digital thread natively through the 3DEXPERIENCE platform, on-premise and on cloud. Our technology developed by significant additive manufacturing technology investment that have been built on top of technology vetted, validated, and used for decades across all industries. And our applications, which with this technology being put together through applications that are model-based, data-driven, and science-backed for enabling you to make parts that really works. Finally, let's talk about validation efforts. Due to the limited time, we cannot show all the validation work, but in short, we validated for different processes, including FFF, SLM, LDED, FDM, EDAM, multi-jet fusion, MJF, SLS, different physics such as temperature, distortion, residual stress and strains, microstructures, and different materials, polymers, metals, or composites. Here's a selected list of the papers that were published last year in the NAFEM's World Conference and the Science in the Age of Experience Conference last year. In addition, additional validation work will be published in this year's Science in the Age of Experience AM Symposium. So in terms of customers, we have worked with DuPont for FFF validation. We have worked with TWI, SIMTech for SLM validation, with Oak Ridge for LDED, with Stratasys for FDM, Purdue for EDAM, HP for multi-jet fusion, and SLS with an automotive OEM. So this is a quick overview of what we validated by end of last year. Distortion prediction is quantitatively validated from coupon test levels to build parts levels for different processes such as SLM, LDED, and different materials, Inconel, titanium, steels of different grade. Another quick review of what we validated by the end of last year for residual stresses, multiple size and interactions, phase transformations, and lack of fusion prediction, as well as grain morphology from phase field simulations. So now let me introduce our continued collaboration work with TWI. So last year, we presented the collaboration work with TWI in terms of predicting location-dependent microstructure features such as grain size, morphology characteristics, and phase transformations and fractions. We did it using a metallurgical model to present phase fractions, cooling rate, and current temperature together with the phenomenological models such as JMA kinetics for diffusional transformation and KM equations for martensitic transformations to predict the phase transformation. Now, this year, we continue that collaboration, and we continue working on calibrating the metallurgical model with embedded thermocouples, validating the grain size predictions and morphology, and mapping of microstructure features and quantities to tensile mechanical properties, simulating the printing, post-processing, heat treatment, and tensile testing of the specimens. So on the left of the slide, we show a number of columns, printing models, and validated metallurgical phase transformation predictions for both the virtual print process and the post-build heat treatment process. Metallurgical phase transformation is simulated predicting the volume fractions of different phases, such as alpha Wittenson, alpha grain boundary, alpha martensitic alpha prime, and then alpha lathe thickness and temperature histories. So these are used to connect with the macroscopic mechanical properties such as Young's modulus and yield stress, also ultimate tensile stresses, etc. We have adopted existing empirical plasticity models to connect yield strength, strain, and ultimate strength, ductility limits to volume fraction content and grain size information. We have done this for a cruciform model to estimate the in the context of Ramberg-Osgood plasticity model, the hardening behavior of as-printed and heat-treated alloys. It is shown that the simulation predicted dog bone tensile test elastic plastic behavior matches those from the experiments. For more information, please come and to our AM symposium in June on June 18th in Boston to listen to the full presentation from TWI. This is another preview to the paper that's going to be published at the AM symposium in June. The main purpose of this SIMTech work is to validate and optimize the process parameters by numerical simulation. Two manufacturing processes are studied, the LDED, laser direct energy deposition, and SLM, selective laser melting. The modeling results are validated through microstructure studies, XRD residual stress measurements, and distortion measurements. For the LDED process, thin wall components are simulated and residual stresses are predicted and compared to XRD residual stress measurements result. It is shown that by using the optimal processing parameters for laser cladding, tensile residual stresses are still generated with a high value and at the starting and ending positions of the wall. Cracks are at the corners and are also observed during sample preparation. For the SLM process, overhanging structures with various support thickness are simulated, and the influence of laser path, time series description, time incrementation, surrounding powder bed, powder material on the resulting stresses distortions are evaluated. Again, for more information, please come to listen to the full presentation by SIMTech at our AM symposium.